All right, pretty big moment. This is our fourth of 4 subspaces for ax equals b, what you've been waiting for. Totoros dig these things, so that's why that character is here. All right, pretty simple. So we had a lot of things just emerge with row space, and that sets us up very easily to play around with this idea that there might be another null space, right? So, so we've just seen, so what left null space is and the connection to the other 3 subspaces. And so these are the, let me fix that up, these are the known unknowns of left null space, the unbuildable reality, right? This is the stuff that if you're thinking and you see things out in the world, these are the things that sleep past you because you don't have building blocks, right? These are the building blocks we're missing. We can't capture them. These are the sounds you can't hear. It's beautiful, beautiful. Of course, well, it's all linear, but it's nice to think about it more generally. So, okay, so we now have these things. We have column space of A, the null space of A, and the row space of A. But we know that that is the column space of A transpose, row space of A. So what about the null space of A transpose? Of course, it's a good thing. Okay, so let's see how this works. And we'll have a little example. We'll work with Inigo just quickly, and then all these big picture pieces are coming soon. But the next piece is the fundamental theorem of linear algebra, which we have almost all the parts of, but we're missing a little bit, which will take the rest of the semester, the rest of this course to get to. We want it, we're going to get it. So this thing is going to be, I'll just say it here so it's not missing. This is the left null space of A. Right? I'm also not left-handed. It's all sitting here with the whole leftness thing. We're not leftists. Left is good. All right? But there was no right, okay? This is not the right null space. This is just null space. So let's figure out why this is called left. So the reason for the name, we've got a matrix, we can find its null space, right? So this is just, what we're doing here is this is just blob, null space of blob, whatever that thing is, and it's a transpose of A. So let's do it. So if Y is in the null space of A transpose, we're going to use Y because now we're in Rm. This is a subspace of Rm. We know null space is fine. We know what its dimension is. We know how to find it. Everything is good. So we can of course find it for A transpose. Okay, so if this is true, then this is the definition. A transpose Y equals 0. Definition, right? And let's look at these pieces exactly. So this is actually, so if A is m by n, just here, then this whole thing is n by m transpose. And this one is an m by 1, so these things match. And this is an n by 0. That's n by 1 to 0, which is an n by 1. So this one lives in Rm, and this one lives in Rn, where there be x's, where the x's are. Right, okay, so why is this, okay, what is this? We know about transposes. Take transpose of both sides. Quick, transpose of A times B is both sides. Let's do that. So nice big friendly parentheses, transpose equals 0 transpose. I'll put it here. B, C, transpose equals C transpose B transpose. Yes. So we're going to use this. And so there's going to be a Y transpose. And then A transpose transpose is just A. It looks like an arrow on top. Let me get rid of this. I mean, it looks like a vector arrow. Okay. Good. So I've swapped places. This is now, again, m by n. That's what we started with. And this is Y transpose, which is 1 by m. This is a row vector. So A multiplies column vectors on the right, and row vectors multiply on the left. And then this equals 0 transpose, which as a whole is a 1 by n, another row vector. Right, so it has this form, if you like, of, let's say like this, blob. Maybe this is an A equals something like blob. Right. All right, so it is a left null vector, right? Y, so all of this is to say that Y multiplies from the left. Y, it's an algebraic thing, multiplies, as we look at it, not A's left out, it's terrible, multiplies A from the left. Very confusing, lefts and rights. And where we're facing, right? So from the left. Oof. Yep. So that's why we're going to say that Y lives in the left null space of A. So in fact, the null space of A is technically it's the right null space of A. You know, we could have said that from the start. We didn't need to hide it, did we? But we did. So in fact, it's the right null space of A because it's A times X equals 0. And this is, this is on the right. Yeah. Okay. So we know all sorts of things about this straight away. We're of course going to think about this equation back here. Right. We're thinking about the null space of A transpose. So what do we know? So we know, okay, we know immediately, all right, maybe with a little thought, but we know immediately from these things that the null space, the dimension of the null space of A transpose, well, it's the number of columns. It's the number of columns of A transpose minus the rank of A transpose. And we know those things in terms of A. They are, it's M minus R, right? Dimension, right, and for NA we have N minus R. It's the number of columns. Okay, awesome. So we know that. And we find it in the same way, right? So we know, so that's a big deal. We find, I have allergy still. We find the null space of A transpose just as we would find the null space of A. Right, so we solve just one example so we just solve A. We're going to call it transpose, we're going to call it Y equals 0. Y is a M plus 1 thing, M by 1, right? This is in Rm. And so let's do an example. So an example is Inigo. Yep, example is Inigo. So it's going to be 1, 2, 2, 4, 1, 2. We would solve it like this: 0, 0, 0. Right? This is A transpose, the 0 vector, solve, solve, solve. But we really know we just need the reduced row echelon form. So this becomes, right, the other two rows disappear because they're just multiples of the first. Right, same plan as always, express pivot variables, pivot vars in terms of free. Right, that's all happening. So the first equation is just, is all that's left, and we have y equals 0, y1 plus 2 times y2 equals 0. So this is pivot, this is free. It's the same, we turn it around. That's still the same problem, right? So don't have to learn anything new, you just have to reframe things a little bit. So we write that as y1 equals minus 2y2, and then we're going to write this, y equals y1. It's going to be the same plan, right? Just put them in, replace the pivot variables in terms of the free. That's it, minus 2y2, y2 equals y2 minus 2, 1. So this is a basis vector because there's only one of them, so that's going to be a basis vector. And this is in, I should say, y2, it can be anything, right? It's a free variable. Good? Good? So let's look, so just as null space and row space divide up Rn, so let's say that, that's important. So just as null space of A and what we now know to be column space divide up Rn, right? So to do the null space of A transpose and the column space of A. Awesome. Awesome, awesome, right? And so we're good, we're good, we're good. Let's draw a little picture just for this one matrix. At this point we just have, so we know the column space is a multiple of 1, 2. Basis for this one was 1, 2. This is a basis. And now we have a basis here, which is minus 2, 1. Minus 2, 1. Basis. And so a big deal is we can see these are orthogonal, right? See these are, right? Take the inner product of those two, minus 2 plus 2. See these are orthogonal. They're 1D and orthogonal. So let's draw their pictures. So 2, 1 is here. Oh, sorry, 1, 2. 1, 2 is here. So this is y1, y2. This is the column space of A. These are the only places A can send X, right? A can only send X to this subspace. And then we've got this other one. We'll give it a different color. It's at right angles, and it is. Okay, so the direction, there's a little basis vector here. So the direction of this is 1, 2. 1, 2. And then we've got minus 2, 1, right? So that's in this direction. Whoops. Minus 2, 1. So any multiple of minus 2, 1, they're rooted at 0, but that's where they are. These are at right angles, so that's an important little thing to put. Very important, right angles. Right, and then we say that A cannot make this. Make these vectors. Can't do it. And in fact, A can't make anything that's not on, let me give it a blue, it cannot make anything that's not here. Right? A cannot make these vectors, or actually A can't reach anything make anything away from, it can make some of it, and that's what we'll get to next, away from the column space of A. So it's not just this red line, right? It's any point out here. So these are out, right? This is out, cannot make it. So there are no solutions if B lives out here, right? So B must live here for a solution. For AX equals B to be solvable, and we'll come back to this example again. If it is there, there'll be infinitely many because this matrix has a null space, right? So there are many things that get sent to 0. I'm going to come back to it. Big deal, left null space. It's the unbuildable reality, right? We actually know, because how our matrices work, that we in fact know these are the known unknowns. These are the things you cannot, if a signal comes in, we know these are ones that we will miss. So it's not quite a Dunning-Kruger situation, but it's pretty solid. So the next piece is the fundamental theorem of linear algebra, most of it, Matrixology. And then there's going to be a series of examples on solving AX, solving for the big picture of AX equals B for 3 examples: the man in black, Inigo, and Fezzik. And so hopefully all of those, and so they get slightly bigger, and the matrix gets bigger, that'll bring everything together for you. But lots of pieces connect. It's one big story. It takes a little while, but believe. Okay.